So we did have this constraint, right, in terms of only one program at a time, but there was the benefit in the sense of having full control, right, full access of memory. But you still had to interrupt, right? And even in general, even modern operating systems, right, have interrupts. If you really have an important program that you need to get right now, then you still may want to interrupt a lesser important program, so you can get it through. But even back in terms of things like DOS systems, right, you have this interrupt mechanism, which especially if you're only going to have one program at a time, right, it is pretty important that you have some sort of mechanism in place to handle this, where you can in general assign, different priority levels for different programs. And, a more important program can halt or interrupt or pause a less important program, and then run that whole more important program all the way through. And then when that's done, you can resume, the lesser important program. And I mean, this could also go more than 2 levels, right? Because you could have different rankings or hierarchies for your programs. And then if any point, the currently running program is running, and then you have a more important program that needs to run, then you can interrupt that program and so on and so forth. And then programs will just resume, a lesser important program will resume when the more important program has finished running. That's kind of the difference between those two. And then another one that sort of combines these two together in essence is what's called virtual 8086 mode. That's another mode. And essentially the idea there is you can be running, on a system in protected mode, for example, Windows 10 or, Mac OS X or whatever. And within that, you can be running a virtual machine that is operating in real address mode, right? And in fact, you could potentially be running multiple virtual machines at the same time that are each in their own, separate virtual environment. So the idea really with virtual 8086 mode is that the overall computer is running in protected mode. And then within that, you have one or more virtual machines that are each running individually in their own real address mode. So in effect, it's a way in which you could, on a modern, computer system with something like Windows 10, for example, it's a way in which you could still ultimately operate in that lower real address mode, right? So the idea being that, going back to some of the things we hit on before, each of those virtual machines would have their own, 20 megabyte address space, and then each of them would still follow the same rules of real address mode, where within that virtual machine, right, only one program at a time. But virtual 8086 is just talking in essence about being able to run things in virtual and real address mode within a computer itself that is still in protected mode. So running virtual machines within the protected mode system, such as Windows 10, and then potentially running multiple of those virtual machines at the same time, with each of them being in their own different real address mode environment. Okay, so that's virtual 8086 mode, just kind of combining essentially the two together by being able to use a virtual machine to run real address mode within protected mode. And then we also have another mode here, system management mode. And so that's kind of really used for things like diagnostics or power management. But that gives us an idea of, the different modes. So we're really primarily, right, focusing for now on real address mode, or on protected mode, because that corresponds, right, again, to any modern operating system. But you can just kind of see how over time, right, how things have changed, how, in the beginning, there was this idea of kind of one program at a time. And so interrupts, of course, are very important if you're only going to have one program at a time. But over time, right, that's evolved to where we're at currently, where not only is it possible to run programs at the same time, but now that's kind of like a basic expectation, right, in the sense that real address mode, right, doesn't really suit the way that we use computers, right, in the modern age, whereas, 30 or so years ago, that's just simply how it was, right? You could run one program at a time. So we've kind of seen over time how things have certainly evolved, right, in, some major ways. And so again, some of the details in terms of, what really makes protected mode work, we'll get into those later when we talk about things like virtual memory. But the big idea for now was this concept of an address space, and then each program having its own address space that is separate from other programs. Whereas with the older type real address mode systems, we had a very different type of picture where it was simply one program at a time and that's it, period. But again, one of the benefits still was that with real address mode, you kind of have that complete low-level control. Which you don't really quite have with protected mode, given that you have, any given program has its own address space and it can't just, access things outside that address space. Whereas in real address mode, your program can access any of those memory locations within that 20-bit address space that it has to work off of. So that's some of the major differences between those different types of modes of operation. Okay, so any questions so far? Okay, so we've hit a lot on, the kind of the basics of memory, registers. We've kind of briefly hit on hardware, but we focused in particular a lot on CPU versus, which includes registers, which are on the CPU, but registers and CPU versus memory. And the idea that in terms of time, right, that accessing a register is certainly preferable over accessing a location in memory, right? Because one is certainly faster than the other, right? Accessing register is faster than accessing memory. And so a modern, really any type of modern operating system has also a caching system in place, what we call cache memory. And the idea is that you think of it as like kind of another layer, another hierarchy, right? Because you have your overall memory, what we sometimes call DRAM or dynamic RAM, and that is not the ideal case, right? In terms of accessing. So in addition to main memory or DRAM, we also have what's called cache memory or static RAM. Right, and in general, it's more expensive to buy and physically install cache memory compared to main memory, which is why we have less of it in general. But the idea is that we can store a limited number of things in cache memory, and the idea is that we can save time if we're able to access it from cache memory and not have to go to the larger DRAM or main memory. So it's another layer, another level of memory, but it's faster than the big, larger thing that we call main memory or DRAM or dynamic RAM. And you can even apply this to multiple levels, right? Meaning you can have, for example, multiple levels of caching to further expand on that concept. And again, the idea is to try and save time, right? We're always thinking about how can we save time, and a caching system is one way to do that. And so the idea is that when you think about memory accesses, and this could be in terms of an instruction, right? So we talked about the fetch, decode, execute cycle, and so in general throughout the time that you're running your program, right, you're doing things like grabbing instructions from memory or grabbing data from memory, right, which is why you have your code segment and your data segment. But if we can store some of these things that we're going to be accessing in cache memory, and then we can access it from the cache instead of the main memory, right, well then we're saving on time, right? So that's a good thing. And now, of course, cache memory is much smaller than main memory, so we have a limited amount of things that we can store in the cache at a given time. And so the idea is that there has to be some sort of mechanism in place where you can, in some sort of logical way, determine what at the current time is going to be in the cache versus what's not going to be in the cache. Because of course, the idea is optimization, right? We're trying to, through the cache, we're trying to minimize the number of times that we have to go all the way to main memory or the DRAM. And so when you think about, for example, things like a loop, right, where you have a loop and which would imply that you have areas of memory, right, that you're going to be accessing over and over. Because, and we'll see loops in chapter 4, right, in terms of how to do a loop at the assembly level, right, with things like the loop instruction. And in general, there's really different ways that you can set up a loop, because we'll look also at the jump instructions in chapter 6. But when you think about a loop, right, the implication is that you're going to be executing the same instructions multiple times. So you could imagine a loop that has an instruction like move EAX-var1 in the body of the loop, and then each time the loop executes, you're going to do that same instruction over and over. If there was no cache system in place, or we weren't using it in kind of a smart, logical way, then each time the loop runs and you execute the instruction move EAX var1, you would have two separate memory accesses where you have to go to main memory, going back to exactly what we talked about with the fetch, decode, execute cycle. The first would be where you grab the instruction itself from the code segment of memory, send the address across the address bus, send the instruction across the data bus, and then when you get to the decode step, you would see that there's the variable var1. So then you'd have to go to var1's location in main memory, send the address across the address bus, send the data value across the data bus, right? And then if there was no caching system, that would all be in terms of main memory. So the idea is that we can apply the cache, first of all, to both code instructions and data values, right? So in general, we can have different types of caches for different types of values. So you can have, for example, a code cache for your instructions, right, to store different instructions. You can also have a data cache to store, data values like the variable var1. But really, the idea, especially in things like a loop, is we don't want to just keep going to that same, area of main memory over and over and over and over every single loop iteration, because that's very far from the ideal case, right? Of course, you can't just do everything off of registers all the time, right? Because we know that registers are limited. Certainly, you have all your various instructions, which are going to have to be stored somewhere in memory. You have variables in general that you have to work with at some point. So yes, right, memory is going to, in general, come into play, but you want to think about how to optimize things, right? And so the idea is we want to have a way in which we can maintain this cache. And the end goal is to try and optimize, from a time standpoint, right? To minimize the number of times that we have to go all the way to main memory. And so one thing that you can think about is, in general, there's different ways to approach this idea of how exactly you're going to go about updating the cache, right? But one thing that you can look at is, well, okay, I have all these different things stored in my cache, but when was the last time that I actually used this instruction or accessed this instruction? If we're talking about a code cache, or if we're looking at a data cache, when was the last time that I actually accessed this variable? Because there's going to come a point, right, where your cache is full and you can't store anything else in there unless you take something out. And so the question is then, well, what is it we're going to take out to make room for the new thing? And so one approach to that is to look at the thing that you used the least recently and remove that from the cache. So essentially, right, if you remove from the cache, that means that you're going to have to, when you access it in the future, it means you're going to have to go all the way to main memory, right? But so kind of downgrade it to main memory, but you remove from the cache, and then the new entry would go in its place in cache. So again, cache is just another type of memory, right? So when we think about a memory diagram, we think of both address, right, and value. Same idea with cache, but it's just physically faster, to access the cache compared to DRAM or main memory. But it's more expensive, which is why we have less of it compared to DRAM or main memory. So the key thing there is just having some sort of system in place to where you're removing and adding things in a logical way to your cache, right? Because you can only have a limited number of things in there at the same time. So one approach is to just look at what was the least recently used and then remove that, right? Another possible approach would be maybe to look at the issue of frequency, which one was used the less number of times overall, and then maybe remove that one. But a common thing is to really look at the issue of recency, because in a lot of programs, right, where we have things like loops, right, that are common, um, you tend to kind of use things that were recently used for a period of time over and over. So looking at the thing that was used the least recently, a lot of times that's going to be a good way to approach this whole idea of how you're going to manage the cache, right, in sort of a optimal way. And again, you can take this general idea of a cache, right, and expand it to multiple levels. So a lot of modern operating systems will have like two layers or two levels of cache. So that just expands the general idea to a cache to another layer, where you might have your top level cache be the best memory access, right? Because in some cases that might be directly on the CPU, right? A little bit of memory directly on the CPU. That'd be your level 1 cache. And then the next level down would be your level 2 cache, which is not as fast to access as level 1, but it's still faster to access than main memory. And you could have a bus to connect the CPU to the level 2 cache. And then after level 2 cache, then you would have your main memory, which is the slowest out of the 3 forms of memory. So that's a common way of handling that, is to have sort of a layered or hierarchical type of system where you have multiple levels of cache, right? And of course, depending on the motherboard and all that, you could even go further potentially with 3 levels and so on and so forth, just depending upon the motherboard and hardware constraints and so forth. But a lot of times we have at least 2 levels to the caching system. So you have your level 1 cache, which would be the best, level 2 cache in the middle, and then your main memory or DRAM at the bottom. So the idea being that first, when you're going to access a variable, like with move EAX bar 1, first thing that you would do is check the level 1 cache. Is it there? If the answer is yes, then great, because that means you don't have to go any further and you just get the value from level 1 cache. If it's not there, then the next thing is you go to the level 2 cache and then check, is it in the level 2 cache? If it is, well, that's still pretty good. That's still a form of cache memory. So then in that case, you would just get it from level 2 cache and bring it in. And if that happens, right, for example, you didn't find it in the level 1 cache, but you did find the level 2 cache, then at that point, right, you might also want to take the, what you just found in level 2 cache and then bring that up into the level 1 cache. So for example, take the least recently used thing in level 1 cache, remove it, and then take the thing that you just found in level 2 cache and move that up into level 1 cache. So that, just applying that idea of least recently used, right, at both levels. Because again, a lot of times when you start executing something, you may be executing that instruction several times, especially if there's things like a loop. So in that sense, it would be good to have it at the highest level. So if we missed it in level 1 cache, but we found it in level 2 cache, then we could just go ahead and in level 1 cache, remove the least recently used entry, and then bring that up into level 1 cache. So that way the next time, the next loop iteration, now we'll be accessing in level 1 cache instead of level 2 cache, right? Of course, it's also possible, because the very first time that you access it, you might miss it in level 1 cache, meaning it's not there, and then go to level 2 cache and it's also not there, and then you go all the way to main memory, right? And then in that case, you could bring it up into, and again, this would depend on how exactly the caching system works, right? For example, maybe if in that case, you might first bring it up into the level 2 cache, and then the next loop iteration, you would miss it again in level 1 cache, access in level 2 cache, and then maybe at that point, you would then move it from level 2 cache all the way up to level 1 cache, right? Just depending upon how exactly it's implemented. But that just kind of gives you an idea of how that would work. So it's a limited amount of things that we can store there. So there is going to be some sort of mechanism or system to managing the cache. And a common way of doing that is to look at the least recently used entry, and then that's the one that you would remove from the cache when you need to make room for something else. Well, a little, yeah, I mean, okay, so yeah, is the speed of the memory somewhat decided by distance between memory location and CPU? Well, in general, memory, yeah, memory is going to always be, meaning main memory is going to be slower than both cache memory and CPU. It's really the hardware, just the way hardware is itself that really determines that. But certainly, I mean, yeah, the closer they are and the less time they have to go across the bus is going to have, you know, a little bit of a impact there. But it's mainly about just kind of the differences in the hardware themselves, right? That a CPU is just physically a faster hardware component compared to the chips that you have for your DRAM or dynamic RAM. So that's kind of the main factor. But yes, in the sense of having, for example, a smaller bus, right? If they're physically a little bit closer together, and that's a little bit less time to, you know, the data has to go across the bus. But the main thing is the actual hardware itself. and again, we'll really officially introduce loops in chapter 4, but the idea is that with a lot of times there's kind of a certain time window where you're going to be accessing, right, the same data or the same instructions over and over, and then once that window is passed, right, maybe you don't need to really access that, you know, that variable, for example, or that instruction anymore. So here, you know, and we'll look at loops really in chapter 4, but if we have a loop like this, where we have, for example, this move instruction, and maybe we're going to do, you know, 1,000 iterations of this loop or something like that, then there's going to be that period of time, right, where you're accessing this instruction, right, over and over and over, and also this variable var1 over and over and over. And so there's kind of this tendency in many cases where when you start to access something for the first time, you're going to be really accessing it for, you know, several times for a certain period of time. And so what would happen, you know, what might happen here in this case is when we start entering this loop and, you know, we want to take this instruction, move EAX var1 and place it in the cache, and then our cache is full, so we're going to have to remove something to make room for it. Well, what we might do then is just look at what's in our cache, and cache is just memory. So you have, you know, if you think about a memory diagram, you've got your addresses and you've got your values at those addresses. And another thing that we would have there also in the cache would be something that would tell you when it was least used, how recently it was used. And what you would do is you would find the entry that was the least recently used, remove that entry, and then add this as the new entry to the cache. So the idea is that on the first iteration of the loop, the very first iteration, right, since you haven't encountered this instruction before, it's going to be in main memory. So you're going to, you know, you would go to the cache, it would miss, and then you go to memory. But as soon as that happens, now we're going to bring it into the cache. So now in the second loop iteration, the third loop iteration, and so on and so forth, we're no longer going to have to go to main memory, right? We're just going to go to cache. But if the cache was already full, then we have to determine what we were going to remove from cache to make room for it. And a very common way of doing that is to just identify the least recently used entry in the cache and remove that. The argument being that in many cases, the one that was the least recently used, right, we may not have to use that for, you know, a long time compared to the other entries in the cache. Main memory. So, and we call that either a cache hit or a cache miss, right? You hear those terms come up. So cache hit is just referring to the case where you did successfully find what you were looking for in the cache. If you looked in the cache and it wasn't there, then we call that a cache miss. So on the first loop iteration, in this case, we would have a cache miss, meaning we did not find it. And so we had to go to main memory, and then if cache was full, remove the least recently used entry, and then bring that in. And so really here, there would actually be two different things going on. We could move the instruction itself, the move instruction into what's called the code cache, which is a cache for storing instructions. And then for the variable var1, right, its value could be moved into a data cache, right? So just different caches for code instructions versus your data values that you're using. So in this case, on the first loop iteration, we're saying that we would miss in both caches. So we'd have to get both the instruction and var1's value from main memory. But we would bring them both into their respective caches, right? The code cache and the data cache. And then on the next loop iteration, we would be able to access both the instruction and var1's value in the caches rather than having to go all the way to main memory. Okay, so that's the gist of kind of the why we have cache. It's just like many other things that we do for optimization purposes. So it is more expensive than your main memory or DRAM, which is why we have such a limited amount of it. But even though it's much more limited in terms compared to DRAM, if we use it in this kind of way, then we can still get, you know, a pretty good boost to performance. Because again, you know, loops, things like loops are very common, and there's going to be that window of time where you're accessing the same thing over and over. And it's a lot better if you're accessing that thing over and over from cache compared to accessing it over and over from your main memory or your you know, or your DRAM. Okay. Okay, so we'll go ahead and go to break here and then resume. So any questions here before we go to break?